Okay, so wait a second. Yeah, so problem one, I know I have to do that. And I wanted to ask a little bit about the simulation problem. And what was there that was bothering anybody? Is there anything? Okay, I'll ask before I start. Are we on?
We are live, but nobody's watching.
Okay, that's not bad. So, are there any topics that I need to add to this list? Yes.
So that question that we supposed to just answer yesterday, question 3. So you know what? I just have an answer to prove both of option are okay. So I just choose one by the way for yesterday, but I'm not sure. I just need like a lot of explanation to be proved like which one is right.
Okay, so this is the one where it asks you what option. Right. So I can talk to the problem.
Yeah, yeah.
Okay. So it's yesterday's assignments.
Yeah, just number 3.
Yeah, yesterday assignment. Assignment number 3. Yeah, that was a good assignment. Oh, and we have Nushin is here, and so I am Archer. Okay, right? So we have. So these are the 4 topics. Is there anything else going on? We're finding that the number of questions we found, like the office hour today, was very quiet. So it's okay. Good. I mean, as long as it means that people are more or less okay with the contents of the course, I'm okay. But if it means that people haven't got a clue, they don't even know what to ask, then I really would like to know. So I know there's only 5 of you here, and there's nobody online.
Oh,
So
no, there's 9 people on.
oh, there's 9 people online. So I want to do a general survey right now. If I had to choose between 2 possible answers, people aren't asking questions because 1, things are more or less okay. That's A. Or B, they haven't got a clue. They don't even know what to ask. Which one would be more correct? A, you're okay. B, class is lost. Because I don't want to find out at the final exam. Right? That's not a good time to find out that people are lost. So can I have a vote between a show of hands here and maybe?
So A is what?
A is things are okay, more or less. The reason we don't have that many questions, people are pretty well, comfortable. Or B, they're totally lost and they don't know what to ask. So this should be maybe an anonymous vote, but it really doesn't matter. This is a safe space. I don't know your names. It really is as secure as it can get. So which one of A and B? Can I have a show of hands here among the 6 of you?
If you want Joanna, check it.
Huh?
You look at the blackboard and Joanna check it.
Oh, you want to, Joanna? You check. Okay, just tell me the number. How many A's and how
We
many?
have 1 A and 2, I feel a little bit lost, halfway lost.
Halfway lost.
Halfway lost.
Okay. So if it's halfway lost, that's okay, halfway lost, then we need to know what area, like what, is it like everything, or is it like a specific topic? Is it like?
Someone had said they're lost in the P chart.
In the P chart. Okay.
We had office hour. Why different?
Yeah, well, it's okay. We can take another office hour tomorrow in the P chart. Okay. So the P chart is questionable. Now, anything else? Anybody here? Should I turn around so that you can vote? Okay, turn around. Joanna, what's the vote here?
Okay, A, you are totally getting it. B, you're lost.
How was C?
C, you're halfway lost. Okay, so I would say more halfway lost. There's maybe a couple I'm lost.
Okay, so then we need to know, not this instant, but I really, really encourage you to, I hope it's not the technology that's stopping you from asking questions at the office hour. I mean, that would really be sad. If you have these questions, you want to ask them, but you're not confident in technology, you don't want to bother, because it's like, it's like calling your long distance to the end of the world and you can hardly hear what's going on. So I hope that with chatting, that's okay. At least you can say what the areas are, and then I can put it on the chart here and I can try to explain more during the tutorials. or during the office hours, you can ask questions. So it's important that we get it. Yes, go ahead.
Okay, I would say the majority is C. The charts are okay, but the probability maths are a bit tough.
The probability
Maths,
math.
yes.
Yeah, the math is tough. Okay, so I just want to say that we're pretty sure that for the final exam, I have posted a link on Piazza. Somebody asked the question, where are the C4 values? And so I went on Googled it, and there's a very nice handout, a PDF that has all the charts and all the equations and everything you ever wanted to know and all the numbers. Did you find that? Did you see it? Anybody see it?
I just, before you, I just sent it from my work and you just sent a complete one, I think.
Okay, and it's very useful, and I think I'll make that accessible to you on the final exam. So that way you know what information. It's almost like it's a crib sheet, an aid sheet for everybody. Okay, so everybody has access to the same information. This course, I'm trying to make it as much as possible to you understanding the material other than memorizing or doing a lot of computations. It's very easy to set this course as a lot of computations and just plugging in numbers. It's a little bit harder to make it so that it checks that you understand. And so the questions are sometimes a little bit tricky to make sure that you understand. Okay. Now, without further ado, I will say this comes first. I will say this comes second. I will say this comes third. I will say fourth. And P-chart, I have to think about it. What specifically, what to do about it. And maybe we could use help in terms of what aspect of the P-chart. I now leave you, Lucian. And you need.
Okay, hi everyone. Today I'm talking about INMR chart. Whenever we give you a set of data, when the sample size is equal to 1, we may or may not mention that it is an INMR chart. Because whenever n is equal to 1, you need to know that it is an INMR chart. You cannot apply x bar s or x bar r chart. So consider the case that we have given you the items. For example, a number of or the measurements. Nine, 8, 10, 18. 9, 10, and it goes up. And then you're using the MR chart because you have samples of size equal to 1. So starting with the MR chart, you need to find. Okay, the first one, remember that the first one is nothing. The second one is the difference between these two. 9 minus 8, 8 minus 10. 18 minus 10, 9 minus 18, 10 minus 9, and it goes on. You can have this. After calculating for example, consider that you have 10 data. If you have 10 data, here you have 9 MR, because the first one is nothing. So, now, you need to have UCL, LCL, and the center line. LCL is equal to 0. And based on the data, you can find the UCL and LCL. Okay, consider that UCL is equal to 6.8, for example. Because the whole data is not given to you, but I consider that it is 6.8. And as you can see, there are 2 out of controls. You have 1, 2, 3, and 10, 9. So there's not to mention it here. Okay, the first one, the difference. For the first one, you don't have any data, so I start with the second one, and the difference is equal to 1. Now consider that CL is equal to 2. So you have a dot here. And then if you continue, you can have 9 dots. And as you can see, sample number data for MR equal to 8 and 9 are out of control. One of them is here, and one of them is here. You can see that. 8 and 9 are greater than 6.8, correct? And the other data are between UCL and LCL. So if you have 2 consecutive dots out of control, what you should do is that you don't need to delete both of them. You need to go to the data, check these 3 data. And as you can see, 18 is the largest value. So if you delete 18, what you have is 1, the difference between 8 and 9, the difference between 10 and 8, and the difference between, so you don't have sample number 4. The difference between 9 and 10, which is equal to 1, and 10 and 9, 1. Okay? So you deleted a point, an individual, and then you have all the data in control. Your UCL and LCL, your UCL and center line will change because you deleted a point. But you deleted just 1 point, not 2 points, although you had 2 out of control. This situation only happens in an MR and I chart. And if you delete a point from MR chart, it will automatically delete it from I chart because you're deleting the data, correct? It's not the situation in a X bar R chart or X bar S chart. So if you delete a point from an MR chart, it will automatically delete it from I chart. It means that in the I chart, instead of 10 data, you have 9 data. Okay? Is there any question? So if you have 2 out of control, they are consecutive. Most of the time, it's needed only to delete 1 of the data, the biggest or the lowest one. So is there any question? For the math calculation, do I have time to talk about it? Okay. One. If we are talking about beta or probability of not detecting the shift, when there is a shift, given that there is a shift. There is a shift means that we go from mu0 to mu1. Okay? There's a shift in the mean, for example. It means that probability of that X bar is between LCL and UCL, given that mu0 has changed. Correct? So, whenever you have X bar, and you're going to find beta, you can normalize it. What you can do is that LCL minus the changed mean, the shifted mean, mu1, over variance of X bar. Variance of X bar is sigma over square root of n. So, if you have a 3 sigma limit, so the final formula is 3 minus k square root of n minus phi of minus 3 minus. But if you don't have a 3 sigma limit, for example, you have a 2.5 sigma limit.
That should be a Z, right? The probability that
Phi.
the next line up. The next line up.
Oh, yes. Sorry about that. So, based on the question, if LCL and UCL is given to you, you can use the formula. If we mentioned that it is a 3 sigma limit, you can use this one, based on the shifted value. K is the shifted value. Mu1 is equal to mu0 plus k sigma. Okay. Another thing is that, can I write here? For the average drawn length. Whenever we are talking about the average drawn length, we have 2 situations. Average drawn length for the in control situation, and average run length of out of control. Okay, average run length of in control is equal to 1 over alpha. Average run length of out of control is 1 over 1 minus beta. So if we give you the shift or the new mean, it means that we have a shift in the process and we want to detect it. So the average run length is for out of control. If the question asks you to find the average run length of in control, you need to, based on the UCL and LCL, for example, if it is a 3 sigma limit, alpha is equal to 3 sigma limit. Alpha equal to 0.0027. Phi. Phi of
Phi is the same as the Excel function normed of this.
probability of z less than or equal to, it is the CDF of a normal distribution. So the other thing is that, so if we ask about the average run length, it may be from in control or out of control. From the question, you can understand that if it is out of control or in control. If it is out of control, first you need to find beta based on the shifted value, based on the formula. Then put it here and can find 1 over 1 minus beta. Can I clean the board? We may ask you to find the proportion of defectives or nonconformities, we say. It is equal to probability of x greater than USL plus probability of x less than LSL. LSL and USL are different from LCL and UCL. LSL and USL will be given to you based on the customer needs. But UCL and LCL are based on the process. So, and look at here, you have x, not x bar. So it is equal to, you need to normalize it. X minus mu over sigma. Because you're talking about x, so variance of x is sigma. Variance of x bar, sorry, a standard deviation of x is sigma. A standard deviation of x bar is sigma over square root of n. So x minus mu over sigma is the standardized value, so it is z. It is equal to probability of z greater than USL minus mu over sigma plus probability of z less than LSL minus mu over sigma. So this is a CDF of the normal distribution. This is 1 minus CDF of the normal distribution, and you can calculate it through Excel. So the difference here from beta is that you are using x and you have sigma. But for beta, you have sigma over square root of n because you're using x bar. Okay? Is there any question?
So this is the fallout.
Yes. Yes, fallouts. Okay, I'm done for today. No question?
So are there any questions on this? There is a, if I make a comment, I mean, I'd like, yeah, go ahead. Oh, okay. Yeah, so just a comment that when you get to expressions like this, I mean, you can also go straight to Excel if you have the USL and the LSL, but then in the Excel function, you need to provide the mean and the standard deviation. So it's 6 of these, have a dozen of the others. You can either standardize. I must say that standardizing is very prevalent because there's only one table in the back of the book for the standard normal distribution. So you always have to standardize if you want to use the table in the back of the book. If you use Excel, you don't always have to standardize. You can go straight to the norm.dist. But I think I think it's always a good way to get presented this material from different angles,
Even if it's somehow there is slight differences, feel free to ask. I'm a strong believer in creating confusion in order for you to learn. I find that when people are confused, they think better, they think more, they ask questions more. Whereas when everything looks so simple, they just sit back and fall asleep. But we do depend on questions. So are there any questions of Wanushin before? Okay. Yeah, thank you. So this is good. These are some of the things that we need to know. The phi is I didn't use phi in the videos. I used the norm.dist.s instead. But I think that's a very good point that that's not covered in the video, that if you have two out of control, adjacent out of control points in the INMR chart, that you only need to remove one. Okay, that was very nice. Okay. Now I'm going back to my list, and so it was more than INMR chart. And yesterday's assignment number 3. Yes, go ahead. Okay, so what we're talking about in capability analysis, there's two issues. There's one issue of getting your variability as small as possible, right? But even if you've tried to get like I may feel that I've produced this umbrella here I've really reduced the variance. But when I go to the market, I find that my competitors are 10 times better than I am, okay? And as a result, the market is saying that my umbrella should be, I allow for some variations. My variability is so much, I've worked years and years to get the variability to really low, like standard deviation of 0.38, okay? And I really feel proud. But when I go to the marketplace, I see that the variability is like 0.1. You know, they're making them who knows where with much better. I said, I don't know how they do it. And so the specification limit for the customer has become narrower or wider than what, like I've been working all these years to get it down to 0.38, and yet this customer doesn't really care. So the specification limit is where you get to find out what the customer wants. The other one is a self-imposed, like I want to reduce my variability because I know generally the customers want lower variability. But now the customer is telling me how much variability, and that variability may not be centered around my mean. That variability may be like 0.5 plus or minus 0.1, and I'm producing at 0.3 because that just happens to be my mean. So I may be off-center. I may not be producing what people want me to produce. So the specification, user specification limit, U is very important. That's what the client wants, okay? That's what the user wants. And that's the only time that it gets in. So does that answer the question? Yeah. That, yes. Right.
And the customer is going to have it 0.5. And you are making that between 0.5.
Okay, so we are making a mu naught of 0.3.
And we are very good, so we are between 0, so we can just make it 0.32. And yeah.
Okay, let's say that that's a student. Oh no, less than that, 0.01. You know, we're very good. We're very good. Between 0.33 and 0.27, right? So. But let's say the customer has 0.8, okay? And so we are far away from, so he may have 0.8 plus or minus 0.2, okay? We're way out of whack. We are reduced our variance around the 0.3, whereas the customer doesn't care about that much about variability as I thought, okay? And he's somewhere else, okay? So this is where the limits that come from the customer have to now be evaluated with relationship to the limits to the control limits. So the control limits, how the control limits relate to the user limits is what capability is all about. And it assumes that your process is in control. Because if my process is out of control, that means that I've got a mess. You know, everything is going wrong and I haven't fixed it. Then you still have to do some more work. You need to have a stable process. Then I can ask myself, okay, this is what I can accomplish. How does that relate to the customer? Okay, yes?
So the question that I believe is important to reinforce the concept of CPE and class since it's extremely important for the industry and maybe grow the normal curve against the USL and LSL.
Okay, so we have in you have in answer to that question, today we introduced capability analysis. That we're then moving to attributes like the P chart, NP chart, C chart, U chart. We'll have a few attribute charts, and then we're coming back much more extensively about capability analysis. So when we come back to the capabilities analysis, we're going to introduce the CP, the CPK, the CPM, all those indices. At this point, we're just introducing the notion of, and maybe pedagogically it's not a good idea, maybe I should adjust on control of variables, control of attributes, and then start with capability. For some reason, the text does it the way of, and Montgomery has been at it for a long time, so I thought maybe that it would be of some value doing that same thing, just introducing it, leaving it, and then coming back to it later. So after we've done the capability analysis, I believe it's tomorrow or Wednesday, then if the question still persists that we may have missed something on the capability analysis, I'd like to hear about it, because we, you know, those indices are very, very heavily used in industry. Yeah, I think I will leave it. I will not attempt to clarify now. I'll wait for when this extended version of capability analysis videos are out. Then if after watching those he still wonders, then I'll step in. Yeah. Okay. Anything else? No. Okay. Good. All right. So now I want to turn to item. Let me remove some of this. So we've done this one, and now yesterday's assignment number 3. Yesterday's assignment number 3, that is day 4, correct? Yeah, I'm bringing all the previous assignments in case anybody's and exercises in case anybody's got any questions. Yeah. So which of the following sample procedures is better in terms of shift detection? Okay. I hope you realize that in order to do problem number 3, you need mu naught and sigma naught, right? And those mu naughts and sigma naughts refer to problems 1 and 2. It's the same situation. Okay, I presume that you guys would come to that conclusion. Then you have a problem, because problem 1, you have access to all 5 observations, right? And you establish a mu naught and a sigma naught from problem 1. You bring it under control, and you now have, there may be some, I don't know if maybe all the points were under control in problem 1 or not. They were. It was all under control. So you have a mu naught and sigma naught for that situation. You also have a mu naught and sigma naught for the second problem, where you only get to see one set of data, only the first column. The question is, which mu naught and sigma naught should you use in problem 3? Did you have that quandary? So there is an issue of perspective here. Like, who has the problem? I know you're given the question because it's an assignment, you need marks and all that stuff. But if you think about it in real terms, you have to think, who's asking? Who wants to know? Whose decision is this? Is it problem 1 decision? Is it the guy in problem 1, or is it the guy in problem 2? If it's the guy in problem 1, you've seen all the data, you will use his mu naught and sigma naught to determine what is better, to get 5 units every 60 minutes or 1 unit every 5 minutes. And how would you decide that? What do you need to calculate in order to decide between option 1 and option 2? Yes? You will only need the difference between, well, you still need a mu naught and a sigma naught. You still need an estimate. But when you say the difference between them, what are you calculating for each option? What do you care about? What difference does it make? 5 units every 60 minutes or 1 unit every 5 minutes? What's the objective of the game?
Can't we use standardized values?
Yeah, but you have to standardize them using a mu naught and a sigma naught. Okay, so the issue is, okay, so the issue is like this.
Okay, sorry, you're benchmarking it.
Yeah.
Can we calculate beta with just K and N? And are ATS and beta required?
ATS, in order to calculate, you're on the right track. You want to get to ATS. Whichever one gives you the lower ATS, the average time to signal is the one that is better. Yes? And ATS is equal to oh, I can write it on here, sorry. ATS is equal to what? To H, like the time, times ARL. And which ARL are we talking about? Out of control. So ARL1 is the one that I'm lazy in terms of writing out of control, in control. So ARL1, okay? And what is ARL1? 1 divided by 1 minus beta. And as you saw before, you can calculate beta from K and N, but you also need, you need to know that you need to standardize. So you need mu naught and sigma naught. Yeah, so you're, okay, so what, right, we have the probability that Z lies between -3 plus and -3 minus. Tell me what it is again. -3 minus K square root of N. And this one here, 3 minus K root of N. Okay, so the question is, N we know. Well, which N are we going to use? Okay, so we have an option. We have 5 units. Either N is 5 units or N is 1 unit. And so at this point, what we're saying then is, and this you can just get straight out of, so what is K? K is equal to 1.5. So what you're telling me is you don't need sigma, you don't need mu. You don't. Thank you. You don't need sigma, you don't need mu. Yes? Okay, thank you. Thank you for proving the teacher wrong. Okay, so you don't need, you can do straight over here. You can then calculate ARL. You can calculate H. You can do 3 independently of problem 1 and problem 2. All right, thank you. Okay, so when I said, oh, you need to be depending on problem 1 and you need to be on problem 2, I sent you all scurrying and confused and all over the place. Are you clear now? Yes, thank you. Is there any question out? Yes.
So at the end of the story, I know that the smaller ATS is better.
Yes.
I just remember that the example that you were doing to just reduce the ATS just step by step in a lecture. But what I'm thinking, ATS is the average time that you get a signal, but that's a false alarm. Right?
No. That signal, all the time you get excess within the bounds, and those are false alarms, because the process has got out of control. The false alarms are within the bounds. Once it's gone out of control, the false alarms are within the bounds, the real alarms are outside the bounds. You're thinking of when you're in control. When you're in control, then the false alarms are outside the bounds. But when you're out of control, then the false alarms are within the bounds.
So why do you call it false alarm?
Well, they're false because it depends on what the truth is. The truth is that the process has shifted, right? If somebody tells you the process, if somebody, God comes out and says, the process has shifted, okay? So now you're waiting to find out how long it's going to take you to find out, okay?
So
Well, Jose, you have to know, you don't know. So,
Can you repeat the question? for
yeah,
someone?
yeah. The question that is being asked is not clear why ATS 1 is what you really want to minimize. I think that's what I hear you saying, okay? It's the average time to signal given that the process is out of control. So I'm designing a chart in such a way that I want to set my frequency and my sample size in such a way that if it's out of control, I will find out quickly, okay? If it's not out of control, I already know, if it's in control, I already know I'm taking a chance of 1/370 that any observation, that it's in control and it will give me a false alarm. Okay, that's set. That's part of the that's part of the plus or minus 3 sigma. So that's been decided. Now what I need to decide is how frequently and what sample size. That leaves the ATS 0 at where it is. You know, ARL 0 stays where it is, but ARL 1 is the one that I can try to now reduce. Yeah?
But you know, I was thinking like this way at first, and then I changed my opinion because one of the reasons ARL is very different. So ARL for the first option is 1.57, for the second option is 1497.
But did you multiply by H also?
No, this one is just ARL. So I was
But the question is ATS, right? You have to decide which one is better, the first one or the second one. So you have to multiply.
according to ARL, right?
No, you can't just decide based on ARL. You have to decide on ATS because you have to the ARL is the number of samples, but then how often, if you sample every week, right? It will take you a long time to find out as compared to sampling every minute. So you have to multiply by that H. If you leave that H out, the whole thing doesn't make much sense. Yes? So you got it? Okay.
There's some backlog.
Yes.
There was no reference in the problem set that the data for questions 1, 2, and 3 are related.
Exactly, and I left that out because I wanted you to figure this out. Okay? It was left as an open thing. Does it have to do? Does it not have to do? And what it has to do with is the aha moment in the video when I said, hey, we can calculate beta without knowing, do you remember that in the video? Hey, sigma's disappeared. Okay, now in the back of my head, that hadn't sunk in yet. So I thought you needed, I thought you needed still, okay? And the aha moment was, hey, you don't need it, and this illustrates it very nicely. Okay, if I said based on problem 1 and 2, then you would really be throwing rocks at me because you don't need it. Okay, and if I say definitely it's independent, then you might, so I left it open-ended.
Okay.
Yes?
Don't you actually mean false approvals?
False
Those
approvals.
false
Yeah, let's, yes, false approvals is correct. And when I get to doing problem 1, we're going to come back to this again, this idea. Okay, so false approvals is when it's out of control. I have my chart, and these points, the student is correct. These are really false approvals. This is a real alarm if it's out of control. Okay, so these are false approvals. I like that. I haven't heard the term before, but that's okay. And this is a true alarm. And if it's in control, then these are true approvals, and these are false alarms. Does that make sense?
I'll let you know in 5, 10
Seconds, okay.
And there's another question. Why can we not get ATS from ATS plus ARK times H?
I don't know what ARK is. ARK? ARK? So
the ARL.
Oh, I see. So, thank you. So what she's asking, why can I get not ATS to be equal to H times? That's what I have. I have H by ARL. So the flow goes like this. You get your beta, you plug the beta in to get your ARL, you get your ARL, you get your ATS. Right? So it goes this way. Like I wrote them this way because that's the bottom line, and then I'm going back, what do I have to do in order to solve this problem? But now that I know, you first calculate that, then you go up there, then you go up there. Yes? Okay. Well, I'm glad I must divulge something to you. Originally, the way the problem was given to me was considering the control charts of problem 1 and 2, do this question. And I wasn't darn sure whether I needed what the role of problems 1 and 2 was, or whether you do 1 or use 2, and I decided just to take it out and give you the question. Okay, so I'm glad we did that. Okay. Is that okay for this item? Okay. Simulation. I will get around to doing problem 4. Simulation. So I spoke today, I went this afternoon, I'm meeting them tomorrow morning at 10 while you're watching the videos, and they think they can do what we want them to do. They're going to create a little website, and on that website will be the link to the simulation model, and you just click on it 1 or 2 clicks, and you would be able to run the simulation. Now, I myself thought the simulation was a good idea to make it more realistic, to make quality control more realistic. But ultimately, you guys are the ones who need to decide. You need to tell me this is a good idea or just a nuisance. So if you think that it's a good idea, then I would like to pursue this. And it's a source of data. Instead of us giving you a set of numbers, it's a source of data. And also, while the course is going on, you can see unexpected things happening, right? You generate the simulation model, you generate the data, different things happening. So I plan to go ahead with the simulation, but I would like to get some feedback as to have you tried to run the simulation at all? Has anybody here, have you all? No, you haven't, because there hasn't been a need, right? So I think we need to give you some exercise that gets you to run the simulation, not for a case where you have to wait hours, right? But a relatively small amount of data that you can then throw into Minitab. I learned a lot of interesting things that came out through using the simulation because it gives you more real data. And therefore, things happen that you may not think of in making up questions, okay? So I plan to do that, and I urge you to try to run the simulation, try to give me some feedback as to what you think it is, whether you think it's just a useless diversion or whether you think it has a role to play in this kind of a course. And I won't be offended, okay? This was, that's fine. So that's that. And now we get to problem 4. Now, you might say, why do we ask you a theoretical question in a practical course like quality control? Well, there is something to be learned from this, and I want to. So you're asked to prove that ARL say that again? Yeah, that is 1 over alpha. That ARL naught is equal to 1 over alpha. Okay, you asked to prove that. Now in the video, I didn't prove it. I just, common sense, I said ARL is in this unit, so alpha is in these units, so ARL is 1 over the transpose, and that's it. You can actually prove it mathematically, and I think there's something to be learned in trying to prove it. The first thing to be learned, I'll get that out of my system, is about series. I don't know if you remember from high school. If you have the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6, can you quickly calculate that? You may remember there's a formula, right, from high school. Well, I don't remember the formula, but I do remember the I really was impressed by this. If you write the series backwards, and then you add up, you get 2s, 7 plus 7 plus 7 plus 7 plus 7 plus 7, right? And how many are there? There are 6 of them, so it's 6 times 7. 42 divided by thing, S is equal to 21. Okay, so those are little tricks with sums and series, which are kind of fun if you happen to if you happen to be an engineer. Okay, there isn't yet. The other one is what happens if you do you know 0.1 plus 0.1 squared plus 0.1 cubed. Is this no, I'm not sure I'm doing the right thing. AR plus AR squared plus, okay, so I say R is 0.1, yeah, plus, plus 0.1 squared, I was right, and 0.1 cubed plus dot, 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 dot. What's that equal to? Right? Now, and this goes forever. This is an infinite series, right? So the trick there is sort of similar to the one before. You multiply this times 0.1. It's not the same trick. It's a related trick, a cousin trick. And you multiply each element times 0.1, so you're going to get 0.1 squared. When you multiply this 0.1 times this 0.1, you get 0.1 squared. And you write it now underneath this guy. This one's going to be 0.1 cubed plus dot, dot, dot. And then you subtract. So you're going to get 0.9 S is equal to 0.1. You with me? And S is equal to 1/9. Okay? And that's it. That's life. Okay. So these things, these kinds of tricks are going to play a role in this proof. Okay? But this doesn't belong in a quality control course, but we'll make use of it. So let's think about this. We're talking about the average run length. Average run length. So let's say that we say let X be a run length. And what we're going to have is that the ARL is really is equal to the expected number, the expected value of X. Okay, run length can be, what is a run length? Okay, well, let's think about this. Let's use this here. Well, let's think of what is the expected value of X. What can happen to X? Can X be, what's the probability that X is equal to 0? What does that mean? That means that as soon as you start, here is your upper and lower and control, this is your center line, UCL and LCL, and you're at 0, okay, you're right there. And where would that, if X is equal to 0, where would that point be? Where would the point be in here? Would it be in between or would it be outside the limits? X equals 0, what is the definition of a run length? So the reason why I think this proof is interesting is it forces you to think about all these fundamentals. What's a run length? We talk about ARL, but can somebody describe in English what the average run length means? It's the average amount of steps, of samples, before you see a what? If we're in control, before you see an alarm. Before you see an alarm. It's the average number of steps before you see an alarm. If it's an average, an expected value, it means it can be 0, it can be 1, it can be 2, it can be 3, and each one of those has a probability. Okay? So we're going back to basics. So what would have to happen for it to be 0? It means that right away I see an X out of there. Okay? Now what's the probability of that X being outside? The thing is in control. We have a Greek letter to describe that probability. Yeah, it's in control. We're at 0, so the process is in control. Alpha is there. Alpha's got to be there. What is alpha? Alpha is the probability that it's in control, but it's outside. It's the false alarm, right? No, it's the false alarm is alpha, right? The false alarm is alpha. That means that if I have a run length of 0, the probability of that happening is alpha, right? So the probability of x being equal to 0 is equal to alpha, right? What's the probability that x is equal to 1? What must happen then? So now I'm at 1. What must have happened if my run length is 1? It must mean that the first one was 1 minus alpha times alpha. It'll be equal to, the first one was in control, the second one jumped out. Yes? Online? Are you there? Are we okay? I know you may not care about this proof, but I think it brings out a lot of fundamental things, and it has something very important to, the message is very important. Probability that x is equal to 2. What must have happened if I'm at 2? What a run length of 2 means that the first 2 were within and the third one is out. Yes? So that means 1 minus alpha squared times alpha. Okay? Now we get the picture. Now, the picture is very interesting because alpha is very small, right? 1 over 370. Right? So which one has the highest probability of it? What's more likely, that it be 0 or that it be 1? 0 is the most likely. Okay? So the most likely thing is that it's small, but the future ones will be even smaller. Right? So the most likely one, if you're going to hit an alarm, it's going to happen now. It's going to be less likely that it happened 1 or 2 or 3 or 4 from now. So what happens? So the most likely is there. Okay. And so if we now have to take the expected value, let me do this. Yeah, it's a type 1 error, correct? Yes, the alpha is the type 1 error, and that's what we're talking about. So if we see this one here, if we see this one here and that one there, then this is a type 1 error, and that has a probability of alpha. Correct? Thank you. And what was the other one?
1 over alpha.
Yeah, 1 over alpha. We're trying to prove this now. Now you might say, why do we want to prove something? Okay. Well, because in the process of proving it, some things come out again that are worth pointing out. That even though the average run length, and that's true for the 1 minus beta as well, even though the average run length may be 42, that's the expected value, it still means all these run lengths are geometrically distributed. Geometric distributions look like what? Geometric distributions, they look like this. Okay? They go out this way. So you can have an ARL, okay, of 1 of 42, but it still means that the most likely thing that you're going to encounter is that you're going to encounter an alarm right away. Okay? But it's just that the expected one is it's worth remembering that these are random variables. Okay, now we're going to take the expected value of x, and that is just equal to, well, alpha times 0, right? It's x times the probability. It'll be 0 times the probability of x equals 0, plus 1 times the probability of x equals 1, plus 2 times dot, 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 dot. So this is equal to 0 times probability 0, that's 0. It's 1 times this, it's 1 minus alpha to the alpha. It's plus 2. There's a 2 there. 2, 1 minus alpha squared times alpha, plus 3, 1 minus alpha cubed times alpha. That's what, plus dot, dot, dot. Okay, that's what we're after. That's the definition. That's the definition of the expected run length. And that's true for expected run length for 0 and 1 also. They each, you can, sorry, that's that, okay? So, well now, this can be solved. This can be solved using the tricks. What should I do? What should I do for a trick in order to solve this? This is E of x. What did I do for the series? I multiply times 1 minus alpha, maybe? If I multiply this times 1 minus alpha, I'm going to get 1 minus alpha squared alpha, and I can put that underneath this, right? So I'm going to do that. I'm going to multiply 1 minus alpha times EX. That's going to be 1 minus alpha squared times what? It's 1 minus alpha times this. So it's 1 minus alpha alpha plus 2 1 minus alpha squared alpha plus dot, dot, dot. Right? This is dot, 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 dot. Okay? Are you with me? Now when I subtract, what am I going to get? It's 1 minus alpha, which gives me alpha, right? So it's going to be alpha EX is equal to 1 minus alpha alpha. What's 2 minus 1? 1. 1 minus alpha squared alpha. What's 3 minus 2? 1. 1 minus alpha cubed. Sorry, this is cubed. Alpha. And so it out. And I can subtract, I can divide both sides by alpha, so the alphas go. And I'm just left by 1 minus alpha plus 1 minus alpha squared plus 1 minus alpha cubed. And we should know by now that the E of x, therefore, is equal to what? Is 1 over 1 minus r. 1 over 1 minus r, that's the geometric series using the little trick, right, that I had before. So 1 over 1 minus r is 1. Actually, it's 1 minus alpha. That's the over. Did I get this wrong? Oh, it's a over 1 minus r. Sorry, it's a over, it's the first, okay, let's, what should I multiply by now? I should multiply by 1 minus alpha. And that's equal to 1 minus alpha squared plus 1 minus alpha cubed, dot, dot, dot. And therefore, for the grand finale, E of x is equal to, is this working out or not? Oh yeah, 1 minus 1 minus alpha is what? Is alpha, right? So it's alpha, E of x, and on what, on that side, what am I going to get? 1 minus alpha. Did this work out or not work out? So did I prove it or not? I made a mistake someplace. Where did I make a mistake? Okay. 1 minus alpha, there we go. Is it time for me to look at my notes? It's 2 minutes to 5, and we're rushing out of here. What is it today? Today is the 5th day, right? Mm-hmm. So I have I failed you? I've proven that expected values is 1 minus alpha over alpha, which isn't quite right. So this is to be fixed. This is where the prof has egg on his face. This is where the prof waits for somebody in the audience to say, you missed something there. It's probability of x equals 1. Probability of x equals 1 is 1 minus alpha times alpha, and then it's 2. That's correct. 3, and so on. So I multiply both by 1 minus alpha, and I get 1 minus alpha squared, and so on. I get 1 minus alpha. That is alpha. So I get that, and I still do this, and all the alphas fall out. And now I have 1 minus alpha, and I have the 1 minus alpha over there. There we go, and that comes out to 1 minus alpha. Okay, problem. Okay, so I have failed you, but I will go back and scratch my head and see where I messed up. I just looked at my notes, and my notes are identical to what I got here, but the last one is gone. So the point of having asked you that, and just to defend myself, the math of the series is not important for this course, okay, I must say. But what is important for the course is to recognize that the ARL is a random variable, not the ARL, that the run length is a random variable. And even though it tells you like 12 is the run length, and so therefore I'm going to expect an alarm in 12 observations, the most likely thing to happen is that if you're out of control, that you'll see it right away. And if you see it in 3 or 4 or 5, it was probably out of control already. So the first out of control signal that you get, even if it's before your average ARL, is you got to take it very seriously because the distributions is like that. And therefore, even if the mean is out there, okay, it doesn't mean that if you see one right away that, no, that couldn't be right. My ARL is 25, and therefore, I don't expect an alarm until 25 samples from now, right? Because that's what my prof taught me, right? I sit around for 12, and, no, don't worry about it. You see one? No, that's way below our ARL. We can let it go, okay? No, you see one, even if it's way below the ARL, you stop the process or bring out the resources to find out what's wrong, okay? Because the most likely thing is that it's going to happen earlier rather than later. It's just that the way expected values work, it gives you the impression that you can wait longer, but you can't. And that's why this is important. And that's that. So tomorrow morning is another day. You're going to finish control. Now, 2 minutes. I just want to say something about the p-chart before I go on. Is that all of these charts are based on the idea that you have a mean and plus or minus 3 standard deviations. That's the only thing you need. It's the mean plus or minus 3 standard deviations. And so you just have to know which distribution. Is this binomially distributed? Is it Poisson distributed? Is it normally distributed? Depending on which distribution is behind the process, that makes the difference as to whether it's P or C or U or you know, we'll have all these various charts, but they're all fundamentally the same thing. Mean plus or minus 3 standard deviations. And that doesn't mean you can't have any questions. You can have questions, and we hope that you ask more questions. And I hope I figure this out. See you tomorrow. What the heck did I do here? How can I?
Says that you did what you did is correct.
What I did is correct, but then I get this. But how do I get that?